Welcome, Advanced Topics students. As promised, here is a review of the process by which we answer the various questions on the review sheet. So I'll have one for both this one, first review sheet, reflecting the first half of the year, and one part two, which of course is on the second half of the year. So let's just dive into it. The question here asks for calculating the wavelength of a piece of radiation, a photon of radiation. They give you the frequency. Well, of course, guys, on the test, you'll be given the formula for this formula for this relationship. It's also written this way as well. It's simply the speed of light, which is given to you as 10 to the 8th meters per second, 3 times 10 to the 8th, equals the product of the wavelength, which is in meters, and the frequency, which is in something called cycles per second. So very simply, you're solving for the frequency, and so you plug in the value for the speed of light and the value for the frequency. You solve, and you try it for yourself. Make sure you get that answer: 1.2 times 10 to the negative 8 meters. Now, for part B, we're again going to use this value for the frequency. The formula we use when we want the energy of a photon and we're given the frequency is the energy of a photon equals something called Planck's constant times the frequency of that photon of electromagnetic radiation. E energy, H Planck's constant. Planck's constant, this will be given to you, is 6.63 times 10 to the negative 34th. And again, we're using the frequency given to us in the question itself. Well, it's just the product of Planck's constant and the given frequency. And you should get an answer of 1.67 times 10 to the negative 17 joules. That's all there is to it. Let's go to number 2. Number 2 is that infamous heat transfer question, in which, here's the assumption that we make. It's that every bit of energy lost by a warmer body is transferred to a cooler body. And so we say that the negative Q, the energy lost by the one body, is equal to the amount of energy gained by the other body. Now, what I did, as you notice here, is I added some diagrams to help me explain. Well, let's read the question first. It says a piece of unknown metal with a mass of 200 grams is heated to 90 degrees Celsius and then dropped into 800 grams of water at 25 degrees Celsius. The final temperature of the mixture is 35 degrees Celsius. What we're solving for is the specific heat of the metal. Well, I summarized the physical data for both of the bodies. Notice that the metal has a mass of 200 grams, as I wrote there. The initial temperature of the metal is 90. And the question that we want to ultimately answer is, what's the specific heat of the metal? The water, on the other hand, we have 800 grams of. You know, or you can easily look up what the specific heat of water is, 4.18. And it says that the initial temperature of the water is 25 degrees Celsius. Okay. Now, what formulas am I going to use here? Well, whenever temperature changes, the Q equation that we use is M times C times delta T. Now, you notice that I have Q lost equals Q gained. So that Q is going to be MC delta T, and that Q is going to be equal to MC delta T. So that's what I wrote here. MC delta T, negative, because that's losing energy, is equal to MC delta T for the other. Just be careful, obviously, into this MC delta T, you're only putting the physical data for the metal, and here you're putting the physical data for the water. Now notice here, I need to figure out the change in temperature. When you take this body and you put it into water, there's going to be a flow of energy out of the metal into the water until here the temperature is equal throughout. So we know that the temperature that it finally reaches is 35 degrees Celsius. The initial temperature of the metal was 90. So then we have a negative change here. a negative 55. Of course, that negative here is negated in a sense, or reversed in its sign. Negative times negative is positive. So you're going to wind up with a positive answer. And when you solve for this, you get an answer of 3.04 joules gram degrees Celsius. Let's move on to 3. Now, question 2 is the question most students dislike. Question 3 is a candidate for the question students most like. Why? Because it's really, really easy. This is called a phase change diagram. It is showing for a given substance what phase the substance will be at a given combination of temperature and pressure. So notice if you're C, these are the combinations of temperature and pressure at which we observe the sample in the solid phase. On the other extreme, A, that's a gas at these combinations of temperatures and pressures. And what comes between is a liquid. There's something called the triple point, which is right here. It's simply the temperature and pressure at which the substance is found in all 3 phases of equilibrium. Kind of think of a foggy slush, the fog being the gas, the slush being the solid and the liquid together. That occurs at negative 15 degrees Celsius. Make sure to write the negative. And at 6 atmospheres. Well, that could not be easier. That's really an easy question. Now, you'll also be asked to figure out what phase changes are occurring. Well, if you've identified the regions correctly, then it's that easy. Notice, if I'm going to go from region C to region B, that means like this. This would be, for example, pressure remaining constant with the temperature going up. Or in this situation, temperature remaining constant and the pressure dropping. When either of these things happen, you're going from a solid to a liquid, which of course you know is called melting. If by comparison, let's say that at a temperature of negative 100, let's say the pressure dropped from 6 to 1 atmospheres, well, in that case, you're going from a solid to a gas, and that would be called sublimation. Number 4, A and B. A asks for the complete electron configuration of a given atom. Your sheet might have both copper and chromium. I'm only focusing on copper here because it makes the point. Well, remember, you first have to figure out how many total electrons there are in the atom. Well, that's the same as the atomic number, 29 electrons. That means I have to place 29 electrons in sp, d, and f orbitals in the first through 7 primary energy levels. Now, there's a pattern for doing it. Of course, you're first going to fill up the first energy level, then go to the second energy level, and go to the third. But there's a question of, in what order do the sublevels fill? Well, if you make our little triangle pattern here, remember I said to you, give me an S, and you said S, give me an SP, SP, give me an SPD, SPD, give me an SPDF, SPDF, go Cyclones. And that was a way of remembering that the first energy level has the S, the second has the S and P, the third has the SPD, the fourth has the SPD and F, and of course you can keep going, but we don't get it go any further than the 5S. I think even the IB only goes about that far. Now, once you have your little triangle set up, we add arrows. Recall here, this upward arrow first tells us we fill the 1s first, and those get 2 electrons, followed by the 2s, followed by the 2p and the 3s, followed by the 3p and the 4s. Notice I don't go directly to the D. Only once I fill the 4s do I come back down, and I can fill up the D and fill up the 4s, and keep going if need be to the 4p and the 5s. And we normally stop there. Notice 29 electrons. I start with the 1s, 1s2. I move to the 2s, 2s2. The 2p, I put 6 more electrons there. 2, 2, 6 is 4. So I've placed 10 of the electrons. I have 19 left to place. I now go to the 3s, and I place 2 there. I have 17 left to place. I now go to the 3p. I place 6 there. I have 11 left to place. I now go to the 4s. I place 2 there. The remaining 9 go in the 3d. Now, this works. This would be your final answer for every element except for Cu and Cr. In the case of Cu, you have to change this to a 4s1, 3d10. If you're dealing with Cr, you are dealing with, originally you'd have 4s2, 3d4, but you'd have to change that to 4s1, 3d5. Now, the next question asks you how many unpaired electrons are there in a copper atom. Well, the first thing you have to realize is that the s, p, and d distribute their electrons over a specific number of orbitals. So if you are s and you have 1 electron, that's represented by 1 up arrow. If you're p and you have 3 electrons, those electrons get distributed 1 per orbital. So in this case, the 3p has 3 unpaired electrons. If you're the d, let's say I'm d6, well, as I said, each one has to have 1 before any can have 2. Those are doubled up, so in this case, I have a total of 4 unpaired electrons. Now, if we go back to the question at hand, the only orbital, the only sublevel that is not full is the 4s. Oh, it only has that 1 electron. That must be unpaired. Thus, this only has 1 unpaired electron. I don't think I'll be able to get done with the full sheet in the 15 minutes allotted, so I'll just tell you that when we get to the point where I finish, that the next question will be included on part 2. This is asking for something called hybridization. You guys have to come in knowing the 5 kinds of hybridization which are here, and know that they correspond to a specific number of non-bonding, effective pairs. An effective pair can be a bonding or a non-bonding region. For example, if we take H2O, H2O has 2 bonding domains and 2 non-bonding domains, so there's a total of 4 effective pairs. Compare that to something like CO2. If I look at the carbon has 2 bonding domains. It doesn't matter that they're double, just that they're bonding domains, and no non-bonding domains. So this has 2 effective pairs. Now, if I ask you about the oxygen atom, well, careful, the oxygen has also that same bonding domain, a non-bonding and a non-bonding domain. So each of the oxygens have 3 effective pairs. So I go here, and I see I have 1, 2, 3, 4 bonding around the nitrogen, no non-bonding. That means 4. That means this has what we call sp3 hybridized. By comparison, something like the carbon on CO2 would be sp hybridized. And of course, the oxygen would have 3 domains, so that would be sp2 hybridized. The last question I think I have time for is part B, which asks for the formal charge on the nitrogen. Well, guys, this is a formula you need to come in knowing. To find the formal charge is equal to the number of valence electrons minus the total number of non-bonding electrons, and again minus the total number of bonds. If you remember, nitrogen, which is 2,5, has 5 valence electrons. If you look back at that diagram, on that nitrogen there are no non-bonding electrons, and there are a total of 4 bonds. So I have to subtract 0 and 4 from 5. That gives me a formal charge on the nitrogen of positive 1. Okay, clock is ticking away. For the last question on this part, I'm going to include that with part 2. I'm going to make that one immediately so you have it at your disposal. So enjoy these. Hopefully this was a profitable way to spend time. Hopefully your questions were answered. I'll see you soon. Bye-bye.